go live.
Well, just at like what, 9 months?
Oh, you just start texting. Okay.
Do you see that?
Start on the back.
1, 2, 3, 4, 5.
Now. Okay. Yeah. Wait, Rahul?
Yeah, we send it back to you.
Rahul! Can you go like a few slides in? Tell me how that looks. Slowly, please.
Okay, it's, it's 7:20, that means that, Evan, Jack, I need you guys, we're gonna go to, direction and
Oh yeah, you see the slides start changing. And
I just say go down.
how are the words? They're hard to see. Yeah? Okay. That was my main concern. Why is it turning red?
Wait, why don't we have a presenter view on this? Like on this, there should be like presenter view where you can see the notes on the side.
Okay.
Yeah, but that's just the way you launch it.
No, I tried to do it. Here.
Usually get like extend rather than 12 more.
Here, look at this. No, it's already on this thing. Or at least right there.
No.
Right, but then,
Rahul,
yes.
I'm gonna pretend you're presenting. I just want to check audio.
This thing presenter view.
No, just like talking.
Oh,
Yeah.
Hi, my name is Lily.
Yeah.
You see how that shows up? That should be there. Regardless.
Thank you.
Hi, my name is Stevie. I'm in my 4th year of mechanical engineering co-op. And I'm also the mechanical team co-lead this year.
Perfect. Thank you.
Yeah. So these are our 2 robots, Ori, which is our existing competition robot, and Arctos, the new robot that we'll be building this year.
Sounds okay.
Do you want me to continue?
Okay. Okay. So it's working? So like once we, can I mute the stream for now? Like
Anyone know how to use presenter
like
view?
have no audio go to the stream for now until we start presenting?
Is that this?
Just because I know there's. Yeah, and a mic aux. Yeah.
So what if I go present to a different screen? Well, that doesn't
started.
Alright, let's get started, everyone. So welcome to ARVP's annual journal meeting. So today we're gonna just kind of go through what our club is about. We'll meet some of the exec member and learn how you can join and what we can do. To start off, so I'm the project lead. My name is Jenny, and I am a fifth-year engineering student, and I will be running this club this year. So this is the rest of our exec team. We are split into 4 different groups. We have the electrical team, which is run by Kirill. We have mechanical, which is led by Stevie and Drew. We have admin, which is run by Rachel and Rahul. Software, which is led by Justin. And, oh wait, electrical is Kirill and Kang.
Yeah.
My bad. Thanks.
And David.
And David. So ARVP, yeah. So our mission statement is basically to promote, develop, and apply the use of robotic system to current and future generations. We're basically building Alberta's autonomous future. So ARVP, we didn't always start with underwater robots. We actually started with land-based. All the way back to 1997, we worked our way through and up until 2018, where we decided that we would switch to an underwater competition. Land-based, super cool, but getting underwater, even better.
Land-based is way too easy, right?
Land-based is too easy,
Yeah.
apparently. So starting from 2008, we started with underwater robot. You can see the latest 3. We have Aqua Ursa, Ori, and this year we're building a whole new robot named Arctos. So the competition, what do we really do? Why do we build underwater robots? So our competition is held every year down in San Diego at a marine base. It's sponsored by the U.S. Naval Office, Space and Naval System Warfare Command, and the Association of Unmanned Vehicle System. So during the competition, it's all about movement and control, vision and environmental awareness, and object manipulation. So you can see here, this is a transect pool that we compete in. It's a massive marine pool. They usually train marine divers in it. And once a year, they clear it out for us to do this competition. So the pool is split into kind of 4 quarters, and each run takes place in a quarter of the pool. So you can see we start off on the yellow square. That's our diving platform. This is where the robot gets put into the pool, and it starts its run. The first task is always some sort of gate that you have to go through. However, every year it changes whether the gate is smaller on one side, bigger on the other side, or there's 2 different colors. And then the next task after that is usually a buoy task. So some years it has been hitting a certain color in a certain order, or hitting 2 dice that add up to a certain number, or hitting the correct picture. So you can see that our vision system is very important when it comes to that. Afterwards, there are sonar pingers under the water leading us to the next task. So here we have a choice. We could either go one route to a pinger with a certain frequency that takes us to the torpedo task, where our robot would shoot torpedoes at targets. Or we could take another route and go more of a manipulation task, where we have to say pick up an object from the bottom of the pool, or move a lever, stuff like that. And to end the competition or end the run off, you surface in a octagon shape, and that ends your run. Or at any point, if your robot surfaces the water, your run is over. So the robot itself, what do we build? So this is our past robot. We are retiring it this year. This is Ori. You can see some of its specifications here. And this year we're going to upgrade it and build a completely new robot named Arctos. So you can see we up the amount of thrusters it has, so it can go faster. It has it's more stable. So you can see that our club generally does pretty well. This is the results from 2019, and you can see that we placed 4th out of 58 international teams, which is pretty exciting. We are competing against teams like Caltech, MIT, Singapore, so lots of international big names. So this is a video from So you can see this is a video from 2017 of the competition. You can kind of see the robot in action underwater.
It's just spread out right away.
Yeah, so you can see that was our run in 2017. We have done much better and done more tasks than what you saw there. So you can see this is our team at RoboSub 2018. It's a lot of fun. So our robot is completely student designed and built, and we have 3 core teams, like design teams. They're mechanical, electrical, and software. And then the backbone supporting all this is the admin team. I'm going to hand it off to the mechanical team to tell you all a little bit about what they do.
All right, awesome. Thank you guys. Thanks everyone for being here. Yeah, I can finish one of those. Just a second. Okay, press the arrow. Yeah. All right, hello everyone. My name is Drew Del Cioco. I am one of the 2 mechanical co-leads for the 2021-2022 season. I'm in my 5th year of mechanical engineering here. I've been a part of ARVP for the past 3 years, one of the mechanical team leads for the past 2. And it's been one of the absolute highlights of my university experience, and I would not trade any of these fine people or this club for the world. So.
I'm Stevie Demeray. I'm the other mechanical co-lead. I'm in my 4th year of mechanical engineering and 3rd year with the club as well. And this is my 1st year as co-lead.
All right, awesome. So let's get into it. So, as Jenny has just told you, we have 2 fantastic robots, Ori and Arctos, our existing, our past, and our present, and our future. Currently, we're in the process of actually getting the fundamental components of Arctos assembled and making the small modifications necessary to take it to competition in 2022. Our robots run about a 3-year development cycle. So we do sort of like a planning phase, then we do like a sort of build phase, and then we iron it out and usually run robots for 2 to 3 years before moving on. As far as like mechanical differences between these 2 robots, there's a few things that I'd really like to point out. First off, as you can see, we went with a substantially different hull design as we had previously. Both of these are actually inspired by the popular show. I mean, I'm sure some of you have probably heard of it, Star Wars. Yeah, so we have a TIE fighter, which is this one, and this is supposed to be an X-wing. Unfortunately, we decided after build production that actually doing a full X-wing would probably be like kind of difficult and maybe increase the drag in a few areas. So we decided to strip it down a little bit and go with a purely skeletal design. Additionally, as far as new systems are concerned, we have the big one this year is this boy over here, our mechanical claw. This has been an ongoing development project for us for a few years, and it's been a really amazing part of the robot to hopefully get this all working in time for competition next year. We also have a couple of other assemblies that are new this year: a cooling system, a balancing system, new droppers, new torpedoes, new everything. And it's been super fun working on this for the last couple of years, getting this in the present to the point where it's in now, I guess.
So the mechanical team is responsible for the physical components of the robot, including the structure, such as the frame and hull, as well as the auxiliary components, such as the mechanical claw, the droppers, and the torpedoes. Mechanical team is also responsible for maintaining and modifying current systems in means of continuous improvement to get the best competition results possible. So this year, our team is working on finishing up designing and building Arctos, including adding in a few new subsystems with the cooling and balancing system, and modifying some others like the claw and torpedoes. We will also be putting the robot through a bunch of testing to iron out flaws, and we will also be starting the design on our next robot this year, later on this year.
Awesome, thanks. So guys, you're probably thinking, all of you guys have spent all of this time during your university career building robots and stuff like that, but I'm not sure that I quite like that. What am I going to get out of this club? Of course, we have a great team of individuals that help each other with homework, that are able to hang out together, and I've made a lot of lifelong friends throughout my experiences with ARVP. But as far as your future engineering career, you probably want to learn something. You want to learn the fundamental engineering skills that will make you a successful engineer. For mechanical specifically, oftentimes this comes down to stuff like SolidWorks. SolidWorks is very foundational. You take a big course on it at MECA 265, and I can't even explain to you how many hours that I've spent in industry just trying to build things on SolidWorks, trying to build very complicated things. We also do a lot with do a lot of manufacturing, using a lot of different manufacturing processes. This can be anything from laser jet cutting to 3D printing to anodizing, the whole works of it. And it's very important that when you're designing stuff, you want to take into account how exactly this thing is going to be manufactured and what manufacturing processes can be used to get the most effective result possible. We also really have a strong focus on the actual fundamental mechanical design process. This is going to be the thing that you're probably going to be spending a fair amount of time in your co-ops learning. I'll go over that probably on the next slide. Also, we do use CFD and FEA, computational fluid dynamics, and finite element analysis, which are two very high-level computational tools that can be utilized to optimize designs for overall success. What is the mechanical design process? Do I have to tap? Okay, they threw animations in this one slide for some reason, but I don't quite know why. Okay, there we go. Perfect, awesome, thank you, Rahul. So basically the first thing we want to do is we want to establish what exactly is it that we're making. We want to do a bunch of background research to figure out what other people have done, or what are the fundamental principles that are going into doing any of our design elements. The next step to it is that we really want to do the fundamental conceptual, then detailed design in order to get the robot to the state that we need it to be in order for us to move it. Then we do a tremendous amount of solid modeling to get fundamental components conceptualized in 3D in the real world. Then at this point we do design reviews, we do analysis. As you can see right here, we have a little bit of finite element analysis going on using one of our tools. in order to optimize our design for computational success. Then we create a bunch of manufacturing drawings. You're going to be probably doing this a lot in industry if you're in MECI. And then we actually do our fundamental assembly process and then test. Of course, there's a lot of feedback loops that go into all of this. We go back around to different steps as needed with each individual component. But basically, any component that we produce goes through this fundamental design process. Our testing and optimization phase is really, really long, and we try and we do as much as we can to ensure that we're at the absolute peak of our possible computational success. I'm going to now hand this over to the amazing electrical team and Kirill, who's going to go through what he does. Okay, sorry. Well, this is the first one on the slide.
Hey everyone, I'm Kirill. I did electrical nano, so if you have questions about nano option in electrical, you can ask me. And then I'm also the electrical team co-lead with this guy.
Hey guys, I'm Kang. I'm a third year electrical engineering student, and it's my second year joining this club, and it's been pretty great. Yeah.
Okay, so as part of the electrical team, there's three main components. You're designing and building printed circuit boards. Printed circuit board is like those green boards that you've seen, like a bunch of components on them, for those who don't know. Then you're managing power and communication wiring, so that's like physical troubleshooting and connecting. And you're also developing and maintaining code for microcontrollers, so firmware, for those of you who are familiar with that. For the electrical projects that are coming up this year, mainly we're focusing on assembling Arctos. We had a bunch of boards ordered before COVID, but then they never got assembled. So we have to assemble them and test them before moving on to newer projects. We have one major research project, the underwater acoustic modem, which is worth a lot of points in the competition, but correspondingly is very difficult to implement. And we have one project right now, which is the Ethernet connection for our Sonar board. And then we're also improving our documentation, which you're probably not that interested in. So this goes to learn embedded system design, basically integrating like different boards, different controllers, electronic components, PCB development and assembly, firmware programming, and soldering. Soldering you probably won't use that much if you go into industry, but embedded system design is something, it's a major field of electrical engineering, so if you're interested in that, then by all means you should join. The tools we use, Eagle, we use that for PCB design. We use LT Spice for simulation to make sure that the board works before we order the parts, and GitHub we mostly use for like background. It's not like software where they use it for like feature development, but you still get to use it.
So as mentioned, we learned about PCB design process, which I think is pretty interesting. So here are just a few steps in the whole process of designing a PCB. So the first thing that you need to do is to research for all the parts and components that you will be needing as per your design requirements. And after gathering all the information and parts needed, you move on to the second step, which is generating a schematic. So a schematic is just like a sheets on Eagle that you put with a bunch of components and make some general connections on it. And then after that, you do some simulation to test out if your circuit works as expected or not. If it does, you will move on to the next step, which is the most exciting step, which is making a board layout. So here, just like placing actual connections and traces on it. It has to adhere to some signal integrity design rules. And after finishing the board, you send it to some manufacturers to manufacture it. And then after it is manufactured, you will solder, basically putting a bunch of components onto it. And then after that, we will verify some connections and operations as well as functionalities. And then I guess the last step is just to program it as per requirement. So, yeah.
And now we're gonna pass it off to the software team to test it.
Sound very good. Hi, my name is Justin, fourth year computer science and statistics double major, and that's my co-lead, Mr. Goat. So software, what is it? Software is responsible for a high level. It's the glue that connects everything together with all the low-level hardware. It's the brain of the whole system. So here you can see Ori ramming an object underwater, and that may seem like a simple task, but there's a whole bunch of other systems involved with performing this. So software can be broken into three major groups: perception, which involves understanding the world around you and using a variety of different sensors. There's planning, which involves a mission plan and making sure that the robot transitions from task to task correctly. And then there's controls, which involves figuring out where you are and where you want to move to. So we've had a lot of success in the past using YOLO, which is a object detection, and we're working on transitioning our image to image segmentation, which is called YOLAT in this case here. And that will allow us to highlight the exact pixels of the object that we're interested in, rather than just drawing a bounding box around something. And with YOLO, it's extremely fast and efficient, and unfortunately with YOLAC, it uses a lot more processing power. And in general, training these models is the easy part. The hard part is getting them to run on the embedded devices quickly and efficiently. And using this computer vision, then we can do a 2D to 3D projection. So if we understand where objects are in space, then we know where we need to maneuver and how to manipulate those objects. We're currently experimenting also using a 3D camera so that we can create better mapping estimates. So our mission planner is the key for the robot to understand what tasks it wants to perform. The mission can be split into multiple tasks, which can be further split into multiple states that the robot can transition between. It's important that the robot must be able to detect when it's completed a task, and also it needs to know when it has timed out onto a task. So if it's not too sure if it's completed a task or not, after a certain amount of time, you just got to say, okay, done, move on to the next one. And our simulator is pretty crucial for when it comes to development, because it gives us an environment to test in where we can't break anything or damage anything. It also allows us to do a lot of things like advanced reverse kinematics for control of an arm, and also has a simulated underwater environment with the hydrodynamics. One ongoing task that we've been working on lately is detecting a sonar underwater. So we've been using statistical methods to try and localize exactly where a ping is coming from very noisy data. So here you can see a whole bunch of estimates, and then eventually it dials in on one spot. This has been working really well in the pool, but as soon as we use it in competition where the pool is, it's not a nice perfect rectangle, then we get a lot more noise, and we still haven't quite solved that problem for competition. And a hugely important part is localization. So the robot has to be able to know where it is in space and know what its position is and what its heading is. We do localization by combining data from various sensors, like a pressure sensor, an IMU, and a DVL. And the DVL gets the velocities on the X, Y, and Z axis. So if you work in localization, you can expect to learn a lot more about sensor fusion and things like Kalman filtering. So if you think about it, like with our robot, it's what you would call a 6 degree of freedom holonomic robot. So it can accelerate on any axis at once. So unlike an airplane, if it wanted to accelerate upwards, it would have to pitch up. But for us, we can use our thrusters to move directly up on the Z-axis. But this comes with a lot of problems and controls. So simple PID controllers are not the easiest to use in these situations, and LQR controllers allow us to do more complex movements like here where the robot's doing a barrel roll. And so all our software runs on the Ubuntu operating system, and all communication is done through ROS. ROS is the robotic operating system. It provides a handful of tools for data transfer, diagnostic, communications. All of our production code is mainly written in C++, but we also do use a little bit of Python and MATLAB. And whenever possible, we like to use the onboard GPU to do CUDA accelerated things for computer vision and computation. And you might want to ask what tasks we have for this year. Unfortunately, not unfortunately, jokes aside, this is probably one of our most important years for software, because our existing code base has been in development for over 5 years, and a lot of the students that wrote most of that code are now graduated and moved on, and they're working in the fields of robotics. And it's getting to the point now where we're maintaining code, and that's not quite as fun. It becomes more of a job, and it's not a hobby, and we want everyone to develop the skills they need. So we've decided to completely upgrade everything to a newer version of ROS, which will involve rewriting the entire software stack. So it's, in my opinion, it's really exciting. So it's my goal to help build a strong foundation both for the robot and for the software members. Starting with the members, that foundation is going to be based around education, providing hands-on training with robots. And for the robot itself, that foundation is going to be built upon, easy to read, production level code with multiple tests and superb documentation. And in general, if we can accomplish localization, a PID or LQR control and computer vision, we'll make top 10 at the competition. And so what are the expectations? As a general rule, we're looking for people that are passionate about robotics and looking for an environment to foster that knowledge. In order to make ARVP great once more, we expect you to be a quick learner and a responsible developer. If you're new to software development, we will provide the education you need to quickly expand your skills. We all started at some point, and my personal philosophy is not knowing something is not a lack of knowledge, it's an opportunity to learn. So yeah, we're all passionate about software. Cool fact is that all of the hackathon competitions, the winning teams always have the ARVP members. And hopefully we can keep that tradition rolling. So with that said, thank you, and hope you consider joining the software team. Up next we have Rahul.
Hey guys, my name is Rahul. I'm in my 4th year of electrical engineering, and I'll be the admin team co-lead this year. My co-lead is Rachel Ellis. She is unfortunately not here, but she's in her 3rd year of software. So the admin team is probably the most fun and the most important team. We're the backbone of the entire club. We handle sponsorships, fundraising, all events and media. So if you've ever heard the ARVP name, which is why I assume most of you are here, then we've done our job right. We also do like a business plan and accounting to make sure we have enough money to A, get a new robot there, make sure team members can go to the competition. We are in a good standing overall, and that in the future, if we need to make another robot, or when we do make another robot, we do also handle getting the money in order to get that done. To best handle our responsibilities, we're divided into 4 sub-teams, which is promotion, logistics, outreach, and treasury. So the promotion sub-team, they look after our social media, any merchandise like these great t-shirts, posters, as well as making connections with the industry. The logistics sub-team is more project management behind the scenes. We look after the website and documentation, but as well as competition logistics. So how will we get to the competition, flights, getting the robot there, so the shipping of the robot, all that. The outreach team, they look after sponsored events, team bonding activities, as well as pool tests. Pool tests are a major part of the club because we need to be able to test the robot in person to see how it would fare at competition. And that's how we know, we need to make this kind of tweak to this particular system. It's great fun and all members are invited. So if you guys do join, make sure to come down to the Buoy Test. To expand on the events, when we do make a new robot, there is a showcase. So the last time for Ori, we had a reveal, a live demo, there was food and a giveaway. We also had media there to get the name out. We also planned like little events throughout the year, like a formal party, or potluck, or bar nights. Of course, all of these are pandemic pending. As you can see, we also have game nights. However, though we can't do that in person, we do have a Minecraft server this year, so it's great fun for everyone. The Treasury Sub Team. This might be the most important part of the admin team. We look after accounting, budgeting, and sponsors. This involves talking to the sponsors, writing the applications for the grants, and it's a fantastic chance for you to get some experience with professional writing, and that's needed in everything you could possibly do after your degree. The admin team, we're responsible for building the brand and creating value to our sponsors. We'd like to ensure that we're known as Alberta's premier robotics organization.
Our members said, you'll learn a lot from us. Skills that you need in industry, skills that you won't learn in your classes. Other than that, it's also just a lot of fun. Don't worry if you don't have any experience. We'll teach you everything you need to know, but please come with a willingness to learn. Don't be scared. I joined in my first year. I knew nothing, and the team taught me everything I need to know. We have a lot of fun here. Pool tests are one of my favorite. It's not every day you get to go swimming with a robot. That's definitely a highlight. And our team, we don't take ourselves too seriously. There's quite a lot of memes that go on. It's a great way to make friends. A lot of my friends are from ARVP. If you're your first year, not really knowing anyone at university, this is a great way to meet people. Even get some homework help. We got people in all different years, all different disciplines. And yeah, like I said, our team we don't take ourselves too seriously. You'll have a lot of fun here. So I will just want to say, thank you for coming out. The next meeting times is here. They will all be held remotely as of now. We want to keep everyone safe and comfortable. We can join our Slack. All our meeting will be posted in Slack. So you probably would have gotten an email from me with a link to join our Slack. All our meetings will be put there. Except for software. Software will actually have their first meeting on September 5th, which is a Saturday, Justin?
Yeah, that's Saturday.
Yeah, a Saturday, September 25th at 11 a.m. in the comp site building, 1-28. We will post that also in our Slack, so everyone knows. But all the other meetings will be held remotely just of right now. And yeah, if you have any questions, feel free to ask them right now. We'll keep an eye on chat as well for the live stream. We can answer questions there. If not, thank you everyone for coming out. It's great to actually see people, and I hope you join us.
Yeah. So we'll make a read the 3 questions that we got in the live chat.
Yeah. If you have questions, you can raise your hand. We can come up to one of the execs
That's an important software question. I was looking at the chat. Doesn't have a 3080.
Our robot's 3080. What?
Yeah, it's basically a
Just keep an eye on it.
I have the answer for the first one.